Hello and welcome back to the course on deep learning. In today's tutorial, we're talking about gradient descent. What we learned previously was that in order for a neural network to learn, what needs to happen is backpropagation. And that is when the error, the difference or the sum of squared differences between y hat and y is backpropagated through the neural network and the weights are adjusted accordingly. So we saw that, and today we're going to learn exactly how these weights are adjusted. So let's have a look. This is our very simple version of a neural network, a perceptron or a single layer feed-forward neural network. And what we can see here is this whole process in action where we've got some input value, then we've got a weight, then a activation function is applied, we get y hat, and then we compare it to the actual value, we calculate the cost function. So how can we minimize the cost function? What can we do about it? Well, one approach to do it is a brute force approach, where we just take lots of different possible weights and look at them and see which one works best. And what we would do is, for instance, we'd try out, for let's say, for example, 1,000 weights, and we'd try them out. We'd get something like this for the cost function, and this is a chart of on the y-axis you have cost function, on the vertical axis, on the horizontal axis you have y hat, and because you can see the formula is y hat minus y squared, this is what the cost function would look, something like that. And basically you'd find the best one is over here. So very simple, very intuitive approach. Why not do this brute force method? Why not just try out 1,000 different 1,000 different parameters or inputs for weights and see which one works the best? You'll find the best one that way. Well, if you have just one weight to optimize, this might work. But as you increase the number of weights, increase the number of synapses in your network, you have to face the curse of dimensionality. And so what is the curse of dimensionality? The best way to describe this or explain it is to just look at a practical example. So remember this example we had when we were talking about how neural networks actually work, where we were building or running a neural network for property evaluation. So this is what it looked like when it was trained up already. Well, when it's not trained, before it's trained, before we know what are the weights, the actual neural network looks like this, right? Because we have all these different possible synapses, and we still have to train up the weights. And here we have a total of 25 weights. So 4 times 5 at the start, plus 5 more from the hidden layer to the output layer, 25 weights total. And let's see how we could possibly brute force 25 weights. It's a very simple neural network right here. Very simple, just one hidden layer. And how could we brute force our way through a neural network of this size? Well, let's do some simple mathematical calculations. We have 25 weights, so that means if we have 1,000 combinations that we're going to test out for every weight, the total number of combinations is 1,000 to the power of 25 or 1,000 or 10 to the power of 75 different combinations. Now let's see how Sunway Taihu Lite, the world's fastest supercomputer as of June 2016, how would it approach this problem, right? So Sunway Taihu Lite, it looks like this. It's a whole huge building pretty much for this one supercomputer, and it got the Guinness World Record for being the fastest supercomputer. Right now, it is the fastest supercomputer in the world, and Sunway Taihu Lite can operate at a speed of 93 petaflops. Flop stands for floating operation per second. So it can do 93 to the power times 10 to the power of 15 floating operations per second. That's how quick it is. In comparison, average computers right now, they do like just over several gigaflops and so on. So like kind of those ranges, way less than Sunway Taihu Lite. So Sunway Taihu Lite is in the forefront of technology. And let's say hypothetically that it can do test one combination for our neural network in one flop, basically in one floating operation. That is not possible. That is not practical because you need multiple floating operations to test out a single weight in your neural network. But even let's give it a head start. Let's say that it can do that in a ideal world. It can do that in one floating operation. It can do one test per one floating operation. That means it will still require 10 to the power of 75 divided by 93 times 10 to the power of 15 seconds to run all of those tests, to brute force through that network. So that means approximately 10 to the power of 58 seconds. And that is the same as 10 to the power of 50 years. That is a huge number. That is longer than the universe has existed. And that is definitely not going to, this number is so huge, it's just definitely not going to work for us at all in our optimization. So there we go. This is a no-no even on the world's fastest supercomputer, Sunway Taiyu Lite. So we have to come up with a different approach. How are we going to find the optimal weight? By the way, our neural network was very simple. What about if the neural network looks like something like this, right? Or even greater than that? Then, yeah, it's just not going to happen at all, ever. So the method we're going to be looking at is called gradient descent, and you may have heard of it already. If not, we will find out what it is right now. So there's our cost function, and now we're going to see how we can come up with a faster way to find the best option. So let's say we start somewhere. You got to start somewhere. So we start over there, and from that point in the top left, what we're going to do is we're going to look at the angle of our cost function at that point. So we're just going to basically, that's why it's called gradient, because you have to differentiate. We're not going to look at the mathematical equations. We will provide some tips on additional reading at the end of the next lecture. But basically, you just need to differentiate, find out what the slope is in that specific point, and find out if the slope is positive or negative. If the slope is negative, like in this case, means that you're going downhill. So to the right is downhill, to the left is uphill. And from there, it means you need to go right. Basically, you need to go downhill. And that's what we're going to do. Vroom. Takes a step, right? The ball rolls down. Again, same thing. You calculate the slope. This time the slope is positive, meaning right is uphill, left is downhill, and you need to go left. And you roll the ball down. And again, you calculate the slope and you roll the ball right. There we go. So that's how you find, in simple terms, that's how you find the best weights, the best situation that minimizes your cost function. Of course, it's not going to be like a ball rolling. It's going to be a very zigzaggy type of approach, but it's easier to remember, or kind of it's more fun to look at it as a ball rolling, but in reality, yes, you just it is going to be like a step-by-step approach, so it's going to be a zigzaggy type of method. Yeah, and also there's lots of other elements to it. There's things like, for instance, why does it go down? Why does it not like go away over the line? So it could have jumped out of this, gone upwards instead of downwards, and things like that. So there are parameters that you can tweak, and again, we will mention where you can find out more on that, and plus we'll have this in the practical application. But in the simplest intuitive approach, this is what is happening. We are getting to the bottom by just understanding which way we need to go. Instead of brute forcing through thousands and thousands and millions and billions and quadrillions of combinations, we can just simply every time have a look at which way is it sloping. So, right, like you imagine you're standing on a hill, which way does it feel that it's going downwards? And whichever way it is going downwards, you just keep walking that way. You take 50 steps that way, and then you assess again. Okay, which way is it going downwards? This way. Okay, now take 50 steps or less, take 40 steps that way. So it gets less and less and less as you get closer. So here's an example of gradient descent applied in a two-dimensional space. So that was a one-dimensional example. Here we have a two-dimensional space for the gradient descent. As you can see, it's getting closer to the minimum. And it's also called gradient descent because you're descending into the minimum of the cost function. And finally, here's the gradient descent applied in 3 dimensions. This is what it looks like if you project it onto 2 dimensions. You can see it's zigzagging its way into the minimum. So there you go. That was gradient descent. In the next tutorial, we'll talk about stochastic gradient descent. It will be a continuation of this tutorial. And I look forward to seeing you there. Until next time, enjoy deep learning.